Hello and welcome to the very first lecture in the chapter 20 of our comprehensive course on AI, ML and DS. The name of the chapter is Practical Statistical Analysis in Python. However, many of these topics in this chapter we have already covered in this chapter, a comprehensive introduction to statistics for data science. Because that chapter extended for 33 lectures or 34 lectures, and for the sake of continuity, I shifted many topics from this 20th chapter to this 19th chapter, and they were discussed in much more depth also. So now in 20th chapter, when same topics will come, at that time we will quickly breeze through them rather than doing a very detailed discussion. So if you are directly jumping into this chapter without doing the 19th chapter, then don't miss 19th chapter, because the heart, brain and soul of data science is discussed in 19th chapter. Okay. Now here, what is the objective of this chapter? The objective is to provide students with practical skills for conducting statistical analysis using Python. And many of these skills were already imparted to you in the previous chapter also. This lecture focuses on using libraries like SciPy and Statsmodels. Again, we have used this library in much depth in previous chapter also, to perform statistical calculations that we have done, conducting hypothesis tests that also we have done in previous chapter, and introducing the basics of linear regression analysis. Now that part is new for this chapter, though here and there some scattered discussion about linear regression was already included in previous chapter and some of the earlier chapter also. But now this time we are officially introducing linear regression. Okay, there are three main parts of the chapter. One, implementing statistical calculations using SciPy and Statsmodels. B part is conducting hypothesis test. So these two parts will be just revision of previous chapters in a way, and this is new, introduction to linear regression analysis. So let us do first part, implementing statistical calculation using SciPy and Statsmodels library. Now here, SciPy and Statsmodel are two most powerful libraries in Python for statistical analysis. SciPy offers a wide range of statistical functions and algorithms, making it ideal for tasks ranging from basic statistics to complex scientific computation. Its name itself is SciPy, so it is actually meant for complex scientific calculations, but it can also handle somewhat basic statistical stuff. But what to do if you want to do some more advanced statistical stuff, like for example ANOVA or chi-square test? That type of tests, they are not available in SciPy. So for that you have to use Statsmodel. So Statsmodel provide more focused functionality for statistical modeling and test. So it is not for scientific computations as such, but exclusively focus on statistical modeling and test. And Statsmodel is an excellent library for econometric and statistical analysis tasks. Now both these libraries offer a wide range of tools for econometric and statistical analysis. So we want to discuss some of the common tasks which can be performed with this library. So first task is descriptive statistics. Second, hypothesis testing. Third, linear regression analysis. Fourth, robust standard errors. Fifth, generalized linear models. Sixth, time series analysis. Seventh, multivariate analysis. Eighth, non-parametric tests. Ninth, survival analysis. And 10th, model diagnostics. 11th, instrument variables IV and two-stage least square regressions. So that is 2S, two-stage LS least square, quantile regression, maximum likelihood estimation, and Bayesian statistics, including Markov chain Monte Carlo simulations. This Markov chain Monte Carlo is very widely used in several sophisticated applications like stock market analysis. It is also used in cyber security for detecting the fraudulent transactions. So it has many applications. But let us start with the first and most basic thing. Now this thing we have already done, that SciPy and Statsmodel provides the facility for conducting descriptive statistics. What is descriptive statistics? Then it is measures of central tendency, that is mean, median and mode, measures of dispersion or spread or variability, that is variance and standard deviation, and measures of distortion in the shape, that is skew and kurtosis. I hardly need to explain anything because we have been discussing these things in the previous lectures, particularly the last lecture. Hypothesis testing. So then t-tests, in which there are three varieties: one sample t-test, independent two sample t-test, and paired t-test. Again, we have discussed in much detail. One lecture of 30 to 40 minutes or more than that was allocated for this, one for this, and one for this in the previous chapter. Chi-square test is used for testing independence for categorical variable. Okay, these also we had done one whole chapter of around 45 minutes or so. Then one whole lecture, that is ANOVA. Also, there are two ANOVA, one way and two way ANOVA for computing means across multiple groups. It can be used for three or more groups also. So that is the biggest advantage of ANOVA. Again, we did detailed discussion for around for 50 minutes or so in the previous chapter. F-test, compare variance and evaluate nested model, for example, in regression analysis. Now, that is something which we have not yet discussed, because regression analysis itself we have not yet discussed. Then, another application of this SciPy and Statsmodels library is in linear regression analysis, in which ordinary least square OLS regression. Now, that we have discussed in a scattered manner here and there, because I had to give the example several times. So we had taken this kind of example, if you remember. Okay, so that is ordinary least square regression. Now we want to study it in proper manner in this chapter. So to get the relationship between dependent and independent variables, and then to provide diagnostic. Diagnostic means how good your line of fit which you have obtained by ordinary least square regression is. What are the parameters by which you can measure the goodness of fit? Then you can measure the goodness of fit with R squared. Don't bother what they are, because we are going to see them. P-value, confidence interval, these two at least we know. Residual plots, that we have not yet seen. So R squared and residual plots, these are two new terms, okay, and that we will be introducing in subsequent topics. Here, this is that ordinary least square regression. The dotted points, they are the data points, and I have to find a line which is the line of best fit, or that is the closest possible line to all the various data points. This line is itself called a model. It is a relation between my dependent variable y and the independent variable x1. So y is equal to beta 0 plus beta 1 into x1 plus or minus epsilon. Now that plus or minus epsilon, because no line comes with 100% perfect fit. So some error comes. So this is that collective error which has come in the entire, this thing is the collective error which has come in entire estimation. No model can be 100% perfect, 100% accurate, right? Now this y equals beta 0, this plus beta 1 into x1, this is itself called ordinary least square regression model. Okay, so and this is called intercept on y-axis, intercept term or constant term of the equation, and this beta 1, this one, that is called slope term. So this is called slope of the equation. Okay, x1 is the independent variable, y is the dependent variable, and this epsilon is the error in the estimation of model. Okay, then that is called ordinary least square regression. How good this model is, that is measured by these parameters, among which some R squared and residual plots. These things are what we are supposed to learn in subsequent topics. Then SciPy and Statsmodels libraries provide robust standard errors. Normally we take standard error as sigma divided by root n, where sigma is the sample standard deviation and n is the number of observations in the sample, right? So sigma by root n, that is what we call standard error. But this has certain issues. So we always write our results with plus or minus sigma by root n, but this has some issues, that this assumes that the distribution is normal and the data has certain quantities, certain rather property which is called homoscedasticity. What is that homoscedasticity? Don't worry at present. But the question is, what to do if data is not normal or data does not have homoscedasticity? That means data has what you call heteroscedasticity. So in that case, standard error is given by some different parameters. This term which gives standard error needs to be adjusted in those kind of cases, right? So at that time, you cannot find standard error by this sigma by root n. You will have to adjust this term. Now the question is how to adjust that term. Then the answer is given by one technique called panel data regression, and that facility is provided in Statsmodels library. Okay, so it handles fixed effects, random effects, and mixed effects model for longitudinal and panel data analysis. Generalized linear model, GLM. Now we have done logistic model for classification. For example, diabetes classification is done by whether the patient will be diabetic or not, or whether the patient will have cancer or not, or whether the customer will churn yes or no, or whether the employee is likely to churn yes or no. Then that thing is done using logistic regression, right? But logistic regression is just one of the several types of linear model. There is actually an entire family of linear models. These are called generalized linear models. So one of them is logistic regression, another is Poisson regression, another is negative binomial regression, another is called probit and logit models. And each is used for different types of data. Logistic regression, I told some examples: customer will churn or not, employee will churn or not, whether the patient has diabetes or not, whether the patient has cancer or not, etc. While Poisson is used to count data or rare event data. For example, how many customers will walk into the restaurants on any random day, or how many technical support calls will come to the call center on any random day. If you want to model that behavior, then you can use Poisson regression. Negative binomial is used for handling over dispersed count data. Now, binomial is used for handling that kind of event which are having only two possible answers, like head and tail. Okay, and similar. But negative, if the data is too dispersed, that is, the dispersion is very high or variance is very high, then instead of binomial, we use the negative binomial model. Similarly, probit and logic models, they are also used to model binary outcomes using some different link functions. So binary outcome is again like this logistic regression only, whether the person has diabetes or not, or whether the customer will churn or not. But here the approach is slightly different with these probit models. Okay, time series analysis. So that is the stock market data, ECG, EEG, then maybe weather data. These are examples of time series data. And to understand this type of data, we can use ARIMA model. ARIMA is auto-regressive. So auto A, regressive R, if I make it capital R, just for the sake of where that word ARIMA is coming, right? So then auto-regressive model. Now there is A, R, I, auto-regressive integrated moving average. So that is why that name of the model is ARIMA. It can model the time series with auto-regression, differencing and moving averages. Very, very useful for predicting stock market data, commodity data, or any financial application where things varies with time. Okay, seasonal decomposition. Then decompose time series data into trend, seasonal, and residual components. Even this we have discussed earlier, that every time series can be broken into three parts. Like this here, this was the diagram which I had drawn earlier. So this is suppose the price of stock or sales of a company, or say sales of a company like Amazon or Flipkart, that kind of e-tailing company, e-tailers. Now this is showing a continuously increasing trend over time. Suppose this is daily data, but over data of last maybe 4 years. So you can imagine that that is 365 multiplied by 4 days data is there, and therefore you can see that the sales continuously keeps on increasing. But this data can be broken into three parts. One is called trend. Trend is like this green light, which shows in general what is happening to the sales. It does not continuously and always goes on increasing. For example, here it increased, but then it decreased also, but then it again increased, then it decreased also. But if you see all tops, like that is like this, then all tops have increasing trend, and even all bottoms also have increasing trend, and these middle value, mean values are also having increasing trend. So that means the trend is upwards. But there are some dips in between coming, because this time series data has also a seasonal component. For example, if it is Amazon Flipkart sale, then in the Diwali or on the Christmas or maybe 26th January, 15th August, the number of time series elements, the number of sales would greatly increase, and thereafter there comes a period, maybe March ending or something, where people are mostly saving money for their tax saving instruments and so on. So there the number of the amount of sales decreases. Then comes next big say holy discount offer, or that way, and then again decreases. So this is trend, this is seasonality, and third component is called noise. This noise is unpredictable part of the data, random noise, and this noise cannot be captured. So that is means that it can be captured graphically, but it cannot be part of your predictive model, right? So then this is what is time series data, and this process which we have done, that original data was this red colored data, but we broke it into three parts, and we study each part separately. That is called decomposition of time series, and we decompose the time series into trend, seasonality, and the residual component. This third noise is also called residual component. Then vector autoregression, model multivariate time series data. This was a simple time series in which on y-axis there was a sales, and on x-axis there was date. Simple, very simple. But sometimes you want to model a more complex time series in which the independent variable depends on 3 or maybe 2, 3, 4 different variables. So if you want to do that kind of time series analysis, then you will have to do vector auto regression. Then Statsmodel provides the facility for that also. Then co-integration tests are done. Now, for long-term relationship between time series variables, certain co-integration tests are required. Long-term relationships means what? That, for example, stock market, if you want to predict price after 2 days, then that is relatively considered easier task. Of course, accuracy may vary, but you can at least predict it with reasonably good certainty. But if you are asked what will be the price of the stock after maybe 2 years, that would be very difficult to predict, because in between some pandemic may come, in between the government tax policy regarding that product may come. Though if it is export oriented company, government may put some ban on it. If it is some service sector company, then government may ban its service. For example, if it is a TikTok, a video platform, right now its growth was phenomenal, and then suddenly US, India, many countries, they put the ban on it like that. So it is possible to it is difficult to study the long term relationship between sales and date, right? But at that time there are certain tests which you can do. One is this Engel-Granger test. Okay, Engel-Granger. I don't know the pronunciation. I'm sorry for that. But test. Okay, so you can do that. That is also provided by Statsmodel library. Now, multivariate analysis. Now, here I will not go into the discussion of this, because we are going to do this in much detail. Any data science course will remain incomplete without doing this principal component analysis or multivariate analysis. So we will do it in much detail, right? Principal component analysis, then factor analysis, and canonical correlation analysis. This is called PCA, this is called FA, and this is called CCA, canonical correlation analysis. Fine. Then there are certain non-parametric tests. So parametric tests are always considered more robust because they are supported by that strong pillar of statistics, which is the central limit theorem. But the question is, what to do if a parametric test does not work? Sometimes you will not find a conclusive result by a parametric test. The reason is that the basic assumptions of the central limit theorem itself are not being obeyed. So in those type of tests, you have to do non-parametric tests, which are, some examples are Mann-Whitney-U test, Kruskal-Wallis test, and this Wick's signed rank test. Okay, we will do this also, because we will take so many different projects and examples. At that time, certain data, you will see that they will be such data that central limit theorem will not be obeyed, and therefore we will have to discuss these tests. But these are also provided by Statsmodel library. Survival analysis. There are Cox proportional hazards model, Kaplan-Meier estimation, and log rank test. These are three tests, okay, which are often used. Then model diagnostics. Now, model diagnostics means you have made a model, fine, but you want to know how good your model is. For example, you made one linear regression model, right? Now you want to know how good this is. What is the goodness of fit of this green colored line? So there must be some parameters which help me to diagnose my model. Or suppose I draw another line of fit. Then the question is, which one is better line of fit? How to decide? So some person says no, compared to the green line, maybe this red colored line. Okay, that means let me plot it using this. This red colored line, that provides better fit, or that provides less error. Another person may say that no, this blue colored line, that provides a better fit, or that means less error. So there must be some quantity by which I can decide which is actually the line of best fit. So there is quantity called R square, sum of squared error. Many more quantities are also there. For example, there are some quantity for estimation of homoscedasticity, autocorrelation, normality. Then these are called residual analysis. So whatever residual remains in any modeling process, how much is the homoscedasticity in them, how much autocorrelation is left, normality, that you can examine the residuals. Then variance inflation factor, VIF. Now we will do a detailed discussion on this variance inflation factor, because it is required for checking multicollinearity in regression model. Multicollinearity is what we are going to discuss in detail, because that is one very important problem with machine learning models, and you have to ensure that the model or the modeling process does not allow multicollinearity to creep in. So at that time we will do this VIF analysis. Then Durbin-Watson test, that is the test for autocorrelation in regression residuals. Okay, so that is also one important thing, that at the end of regression process you will find some residuals that you have to find how much autocorrelation is still left in that. Okay, then instrument variables and two-stage least square. Now these are two advanced things, and we will not be requiring them anywhere, but at least you should have heard the name. Okay, so they are used for estimating models when there are endogenous predictors. Okay, and quantile regression model, the conditional quantiles, for example median or other quantiles, instead of mean, useful for understanding distributional impact of predictors. So instead of regressing over mean, we will be using regression over median. That is called quantile regression. We will be doing that in detail. Maximum likelihood estimation, again we will be discussing that in much detail, so I'm not discussing at present. Bayesian statistics, some Bayesian statistics we already discussed earlier, the posterior probability and everything, but Markov chain Monte Carlo simulations we have not done. We will be doing them in this time series example, right? So there are certain methods like deep sampling or Metropolis Hastings for posterior inference in Bayesian models. These methods are also provided by Statsmodels library. Along with there are certain other which are other library PyMC3, MC for Monte Carlo, right? So Statsmodels provide Bayesian functionality while this PyMC3 is required for Monte Carlo simulation. So you can see that just like we have done pandas and numpy and they are extremely powerful libraries, then we took 2 chapters on study of NumPy, 3 chapters on study of pandas, and so on. Similarly, the SciPy and Statsmodel, they are also extremely powerful libraries. But we don't need to put 2 chapters or 3 chapters on SciPy and then 3 chapters on Statsmodel, because out of these things, which describe the functionality of SciPy and Statsmodel, around 99% or maybe 99 is a little bit high, but 95% of the discussion will be covered when we discuss machine learning models. Okay, so at that time these things are already covered, and I will point out that see that we had seen in chapter 20. Now this thing is getting covered here, and we may not cover it by using Statsmodel or SciPy library. We will use some packages like XGBoost or Random Forest or neural networks or maybe other methods for machine learning, but they internally somewhere will be using some of these features. So I will point out where those features are being used. And since you don't have to bother, that is the biggest advantage with packages, that once you import this PyMC3, you don't have to bother how internally Markov chain Monte Carlo works. You just have to learn how to use this package for different types of data, right? So in next lecture, lecture 2 of chapter 20, we would be doing one example out of the several examples where NumPy and Statsmodel are used for econometric, and statistical analysis. Okay, so which example we will be doing? Then we will be doing this example, because this is the most useful example from data science point of view, and it will naturally lead us to the next chapter where we will be starting our actual data science, that is simple linear regression. So this topic we will start in next chapter. Still the next chapter would be advanced statistics. Okay, and at that time you can see here we are handling that multicollinearity. So that is this multicollinearity word was there here somewhere. Here variance inflation factor and check for multicollinearity in regression model. So as I said, there is no need to discuss all these things in this chapter, because somewhere in subsequent chapter many of these topics are going to come. So we will start with ordinary least square regression. Okay, so if you have not done this, then you can do that. I have already installed it. So under that is exclamation and pip install Statsmodels. And if you have not installed SciPy, then leave a space after Statsmodel and use install SciPy also, right? So because now we will be dealing with these libraries in our next lecture. So see you in lecture 2. Thank you.